In this video, we're going to look at the introduction to our conics, and we've studied conics before in the past, looking at them in terms of second degree equations, and here we're going to look at them in terms of a plane that is intersecting a double napped cone. And we can see here that if we take the plane in this first picture on the left, we're going to end up with a circle because when we take the plane straight through the cone here, the intersection is a circle here in the middle. And then for the second one, if we notice, if we put a little bit of a slant in this yellow plane, then we can see that we're going to end up with the ellipse that is formed by the intersection. And for the third one, the one we're probably most common with is the parabola. And again, if we put more of a slant here where the intersection of the plane is going up through the side of the cone and then up through the top, we can end up with the parabola here as our intersection. And then the last one, if we take the plane here that's in green, notice it goes through the top and the bottom, and we're going to get the hyperbola. And that's kind of a similar shape to the parabola, but we get part of the graph that is opening up and down due to the intersection of the top part of our cone here and then on the bottom part for the intersection. So in this video, I'm just going to kind of introduce another way that we can look at studying these conics. So the first way we looked in the past was looking at a second degree equation, and here we're looking at the intersection of this double nap cone. And now we're going to study another way that we can look at the circle, the ellipse, the parabola, and the hyperbola by using what we call a locus or collection of points that will satisfy a geometric property. And what that means is we're going to basically describe some type of property using the collection of points to describe the circle, an ellipse, parabola, or hyperbola. So if we look at this first example here of using this idea of our locus of points, the example says we have the collection of all points x, y equidistant from a fixed point h and k. So let me read that again. We're looking at a collection of all the points x and y. So all the points here x and y that make up our shape here that are going to be equidistant from a fixed point h and k. Now at this point, maybe pause the video and see if you can determine what we're describing here. All right, hopefully you were able to figure out this shape. If we look at this carefully, we have a fixed point h and k. So that means here we have a point that is not going to move. And we want the collection of all points that are equidistant from this point. So that means we're going to go out a fixed distance, and then we're going to look at all of the points. So if we look at a point here, and if we went another fixed distance, or the same fixed distance rather, then we would have another point, and we could keep doing that if we kept going out all these different the same fixed distance each time. And this may not be exactly right, but if we do that and we have the points here for each one of these, then we can see that we're going to end up with a circle. Because here, our fixed point that we have is actually representing the center of our circle, and then of course the equidistance from that is looking at the radius of our circle. And then of course all of the points that fall on the circle, all these points that actually make up the circle, that would be all the points that we're describing here for x and y. So this is an example of how we can describe this circle by using this description here, this locus or collection of points. The other way is up here we looked at the cone. We could describe it as the intersection here, and this intersection gives us the circle here if we cut the intersection straight through the cone. And if we think back to the past when we talked about a circle, the other way we could describe this is by using an equation such as x squared, and see if you remember this one, or well, let's make it this way. We would have x minus h squared plus y minus k squared equals r squared. So this is going to give you the equation for our circle. And of course here again we have our h and k, if you recall. That's going to represent the center. So h and k is the center of our circle. And then of course r is going to represent the radius. So if we had the following example over here, let's say that we had x minus 2 squared plus y plus 3, and the quantity squared is equal to 16. So if we want to identify the center of this circle, we could identify h and k. And if you look at the formula here, because there's a negative sign already in the formula, then that means this is x minus 2, so that means the h value has to be a positive 2. And another way to think of this, I like to kind of mentally think of setting what's in the parentheses, the x minus 2 equal to 0, and if we were to solve that for x, then we would end up with x is equal to a positive 2 for our h, and then over here for the k value, we could do the same thing. We could mentally think of y plus 3, setting that equal to 0, so that means our y coordinate, which would be the k, would be equal to a negative 3. So we end up with a point 2, negative 3 for our center. And once again, that's because if we look at the formula, it has this negative sign already in it. So technically that means this would be y to get a positive minus negative 3 squared. So this is showing us because of the negative sign is already here in the equation, then our 3 must be negative because the two negatives would make it y plus 3. And that's why up here we can simply solve for that by setting that equation up here equal to 0. So there we have a center of 2, negative 3, and then the radius, because this is equal to r squared, then that means r must be equal to the square root of 16, which would simply be 4. All right, so now in the next several videos, we're going to look at the ellipse, the parabola, and the hyperbola. And we're going to start off with looking at the ellipse, and we're going to study how, I think we're going to start off looking at the parabola next, and we can study how we can describe this as using this idea of locus, or a collection of our points that will satisfy a geometric property.